Hi, so in this video I want to talk about concurrency concepts in Python. And there's not going to be any code in this video. Basically, I want to talk about all these different concepts and maybe clarify certain things, especially the difference between multiprocessing, multithreading, asynchronous programming. What are the pros and cons or the strengths and weaknesses of each one of those, and when would you use them? Because I think there's a lot of confusion there. And I've done a video before on multithreading and shown that multithreading doesn't speed anything up necessarily, right? It's not a magic bullet that's just going to speed up your application. So we're going to talk about that, and we're going to talk about why that's the case as well. So we're going to talk about concurrency. What is concurrency? Then we're going to talk about processes and threads. And then we'll talk about time slicing or interleaving and parallelism. Then we'll look at the thread scheduler very quickly, the operating system thread scheduler, what its task is, what it does. We'll talk about the Python global interpreter lock. Then we'll look at CPU versus IO-bound workloads, because this is really where it matters. The kind of work, the kind of, things that your application is performing, whether they can be sped up using multi-threading or asynchronous programming or multiprocessing, very much depends on the kind of workload that you have. So we need to be able to identify those and understand them. Then we'll talk about preemptive versus cooperative multitasking. And then finally, we'll take a look at async programming and where that fits in to all this. So let's talk about concurrency first. Concurrency is a concept. So it is how a program or an algorithm is structured. It has nothing to do with how that program is being executed. It is merely different ways. And that's because there are different ways of executing concurrent code. So an algorithm is concurrent when it is structured into several subparts that can be executed out of order or partially ordered, but really we want out of order without affecting the outcome. Now the code sections therefore are not necessarily executed in a specific order, but the final results remain the same. That's kind of key to concurrency. So let's take a look at an example. Suppose we want to average a list of n numbers. Let's say we have x0 through xn. Now here's the sequential algorithm. We just add all the numbers up. Let's say that's the sum of the numbers. Then we count all the numbers. Let's call it count. So in Python, you might do something like sum of that. You probably wouldn't use sum as the variable name here, but this is conceptual. So you would sum up all the elements of the list. You would count all the elements of the list, and then you would calculate your average as being the sum divided by the count. These operations are being performed sequentially. Now, on the other hand, how could we make this algorithm into a concurrent algorithm? Well, we could split the list into chunks. Let's say we split it into 3 chunks. We could split it into more or less, it doesn't matter. But the idea is we take this list, we split it into chunks, and then we calculate the sum and the count for each one of those. Now you'll notice that I'm not saying we're executing that in parallel or we're executing those sequentially. I'm not talking about the execution. I'm merely talking about the fact that we are breaking up essentially our list into 3 chunks, and we are now able to calculate the sum and count for each chunk. And so those are the concurrent computations. They're also called modules, but I'm not going to use the word module. I'm going to use the term fragment, because module in the context of Python could be confusing. You could think of it as a Python module. This is not what this is. So we have these 3 concurrent computations, these 3 concurrent fragments. And once we've calculated the values for each fragment, sum 1, sum 2, sum 3, count 1, count 2, count 3, we can then gather those results back and calculate the average by taking sum 1 plus sum 2 plus sum 3 divided by count 1 plus 2 plus 3. So that's a concurrent algorithm. So you can see that it's a conceptual thing. It has to do with how you structure the algorithm, how you structure the code that you're going to run. concurrency doesn't say anything about how this is going to be executed. And the important thing here is that no matter the order of execution of the concurrent fragments, the final result is still the same. So it doesn't matter if we execute this fragment, then this fragment, then this fragment, or a different order, we'll still arrive at the correct final average in the end. And that's really important. So now we know what concurrency is, but how are concurrent fragments executed? Well, one way of doing it is indeed parallel execution. So you have fragment 1, 2, and 3 that we had in our example. And so what happens is that you could use CPU 1 to run fragment 1. At the same time, fragment 2 could be running on a second CPU or a second core, but it's doing it at the same time. And then at the same time, we could run fragment 3 on CPU number 3. So this is parallel execution of the concurrent fragments. And of course, it requires multiple CPUs or cores. And it also requires that the code executor be able to take advantage of these multiple CPUs and cores. But that's one way of executing concurrent fragments. We can do it in parallel. Another way of doing it is using this time-sliced execution. So again, we have those 3 fragments, 1, 2, and 3, and we have our time scale. So what happens is that we can actually run this on a single CPU. We do not need multiple CPUs for this. And the way it works is that fragment 1 is going to execute for a certain amount of time. Then it's going to switch, and fragment 3 maybe is going to execute for a certain amount of time. And then we're going to switch again, and fragment 2 now is going to execute its code for a little while. And then it's going to go back to maybe fragment 1 and execute for a bit. Then it's going to go to fragment 2 and execute for a bit. And then maybe fragment 3. And this happens so fast on our computers that when we look at the execution of fragment 1, 2, and 3, it looks like it's happening in parallel, that it's happening at the same time. But in fact, it's not. It's being time sliced that way. So we only need really a single CPU or core to do something like this. Now, every time the execution is paused, right, when fragment 1 starts running its calculations, let's say those sums and counts, and it gets interrupted and something else is going to run, well, this current state of that code must be saved somewhere. And then every time the execution is resumed, when fragment 1 resumes, let's say over here, well, that previous state needs to be reloaded so that the code can continue executing from that point. And this is something called context switching. Now, each context switch has a performance cost. If you think, every time you context switch, you have to save the state of the current fragment, the current thing that's running, and then you have to load the state for the new thing that's going to start running again. So there's a performance cost, there's a performance penalty that we have to pay whenever this context switching. Now, this time-sliced execution is also very commonly called interleaving. So let's talk about processes. So think of a process as an application instance executing in your OS, like Excel and a web browser and a Python app. Now, all these are running at the same time. So these processes are running concurrently, right? They're running at the same time. Now, they may run in parallel on a machine with multiple CPUs or cores, or they may be using interleaving or time slicing. Even on a multi-CPU core machine, you might still have processes that are running using time slicing. Let's say that you have 2 cores on your machine or 2 CPUs, and you're running Excel, a web browser, and a Python app. Well, right, you can't possibly be running them in parallel, in pure parallel mode, because you have 3 processes running and only 2 cores. So you're going to be time slicing somewhere as well. So very often that's what happens when we have multiple cores and multiple processes. They are running in parallel, potentially, but they're also running using interleaving or time slicing. Now, the important thing here is that each process runs independently. The memory is not shared between the processes as well as other resources, but mainly let's talk about memory and data. When you're running Excel in your web browser, they're not sharing the same data, right? They don't have the same data and the same global variables and things like that. Same thing with your Python app. So that's an important distinction about processes. They're independent and memory is not shared between them. Now, if you think about processes, there's really three possible states to a process. It could be running, which means it has access to CPU and is actually currently executing code. That means the process is running. It could be ready, which means that it's basically paused. It could run if it had access to a CPU, but it doesn't have access to the CPU yet, right? It's been halted basically, and it's waiting to continue running. But the other important state is that it could be blocked. Your process could be waiting for something to happen before it can continue. So even though it may have access to a CPU, it can't run because it's waiting for something to happen. For example, an I/O operation, such as receiving data from a web API. Let's say that you have code that makes a call to a web API. Well, it needs to wait for that result before it can, continue doing the processing based now on the data that was returned. That's called blocked, and that's something that's really important. It's going to come up again and again in this discussion. So what are threads? Well, each process is executing using one or more threads, and at least that's the way it works in most modern operating systems. Processes don't run. The way processes run is that they have one or more thread, and that thread of execution is what's actually running the code that keeps the process moving forward. So we always basically start with at least one thread, which is often called the main thread. And this thread now has this global data, this shared state that's essentially for the process as a whole. But all these threads have access to this global data. So concurrent code in our process can be executed using multiple threads, right? And this is called a multi-threaded process. Now, if we don't use multiple threads, like in our Python application, if we don't do multi-threading, if we just basically do plain, Python development, then we are working with a single thread, the main thread, and that's called a single-threaded process. So threads have access to the shared resources in the process, the global data, the open files, etc. So if you think of a Python application, you have variables. Maybe you've got a global variable in your module. You've got multiple threads running. They all have access directly to that global data. That's very important because in processes, you don't have that. But within a process, the threads do have access to the shared resources. Now, you can also have private resources for each thread, like local, think local variables to each thread, and they're sometimes called thread local data. And that's fine. That works as well. We use that all the time. But the more important thing is this access to the shared global data. So how are those threads going to run? Well, they may run in parallel on a machine with multiple CPUs or cores. And they could also be using time slicing and interleaving, even on a multi-CPU core machine, just like with, we said that about processes, but now we have to realize that processes are really running because threads are running. So the threads could be run in parallel, or they could be using time slicing. It kind of depends. And it kind of depends on what? Well, how many cores or CPUs do you have? And is the executor that's running the code able to take advantage of the multiple CPUs and cores? That's critical as well. So how do these threads run? How do they get stopped and restarted and so on? Well, that's called scheduling of threads. The operating system has a piece of software called the thread scheduler, or just the scheduler. It decides when to run threads. And it has some intelligence built into it. So it knows that if a thread, let's say, is waiting for I/O on a socket, it knows that that's a good time to switch the thread and run some other thread because you're waiting anyway. So remember that multiple running processes results in multiple threads. Even if each process is single-threaded, the scheduler still has to basically be able to run threads. So the scheduler runs, pauses, and restarts threads all the time. It happens very fast, but it happens all the time. What's important is that the scheduler decides when to do that, not us as the application developer. If we're writing a multi-threaded application, we don't really get to decide when that thread is going to get paused and when the other one's going to get started. That's the scheduler that does that. And the scheduler really has no knowledge of the code that we're running, right, of our logic. So when a thread is paused, its current state must be saved in memory. That's actually a lot of work. There's a lot of things in the state that has to be saved. You know, it could be main memory, it could be cache memory on the CPU, a bunch of things has to be saved somewhere. So when a thread is resumed, its original saved state must also be restored at that point. And that is also a lot of work. And as I mentioned before, this is something called context switching. And it has a definite performance penalty. If you're running a piece of code, is it faster to just run the piece of code? Or is it faster to run the piece of code a little bit, save the state, wait, and then reload the state, run it a little bit more, and keep doing that? Yeah, obviously, you're getting a performance penalty from the context switching. So when the scheduler pauses a thread and runs another thread, we say that the scheduler preempts the thread, and hence the term preemptive multitasking. So again, as a takeaway here, context switching has a performance penalty, and the scheduler decides when to do a context switch, not us. So I use the term multitasking as well. So it's a general term used to denote that multiple things are running concurrently. It could be multiple processes, like running Excel, a Python app, and a browser at the same time. It could be multiple threads, or really any other way of running code fragments concurrently. Now note how I use the term concurrent, not parallel. So multitasking again is more of a conceptual thing where we're running multiple things concurrently. It doesn't mean in parallel. It could be performed in other ways as well. So next, let's talk about the Python Global Interpreter lock. It's also called the GIL for short. So the way CPython is written, and you have to remember that different Python implementations may do things differently. I'm talking about the canonical Python, the CPython. The way it's written, it only allows for interleaved or time-sliced running of multiple threads. The GIL basically is this global interpreter lock, and even if we create multiple threads, basically what the GIL forces is that only one thread is allowed to run at a time. So there is no parallelism when we do multi-threading in Python. None. It does not take advantage, therefore, of multiple CPUs or cores. It's basically just time slicing. Now, why was it done? Well, it makes writing the CPython interpreter itself, right, the CPython interpreter, easier. It actually speeds up single-threaded processes, which is how most Python apps are written. Most of the Python apps that we write, we're not using multi-threading. We're just writing regular Python apps. There's no multi-threading, nothing. And if the GIL was removed, and it's been tried, there have been attempts to remove the GIL, it's been called the gilectomy, but none have been accepted yet. And one of the main reasons why is the speed, the performance hit that it basically causes. Because now, if you remove the GIL, you have to make all of Python thread safe. And there's a lot of things that have to happen. And, there's context switching, obviously, as well. But that's not as important as all the things that need to be put in place to lock resources so that you're not, threads are not stepping over each other. There's a bunch of stuff, that needs to happen. And that slows everything down. And so that's why it hasn't been done until now. I don't know. There is another proposal for removing the GIL from Python, from CPython. We'll see if it happens or not. But as of this video, if you are using multithreading in Python, be aware there is no parallelism, and you therefore do not take advantage of multiple CPUs and cores. So let's look at another approach to multitasking. We saw that the scheduler implements preemptive multithreading. So we don't really have much say over when one thread is stopped and another started. And this can be difficult when using shared resources. And you have to take a lot of care to ensure that things run as expected, even if the task is being interrupted preemptively. That's a problem, right? Now, another approach is to write code where we explicitly say when, or really where, a task can be interrupted to allow another task to run concurrently. And this is called cooperative multitasking. It's cooperative because we do not let the OS preempt our concurrent code. We specifically say when we write the concurrent code, hey, if you want to pause the execution of this fragment here at this point, that's fine. But if we don't do that, then it's not going to switch the fragment and run another one. We have to be very explicit about where that can happen. So this can be really useful in cases where a code fragment is waiting on an external resource to complete and return something. Maybe it's waiting for a database response. Maybe it's waiting for a file to be opened and read by the operating system. Maybe it's waiting for a response from the web API. If you think about these scenarios here, it's a good point if you're waiting for those responses, that's a good point to say, hey, by the way, if you want to go and run something else now, that's fine, because anyways, I have to wait for this data to come back. It could even be waiting for another process to return something. Maybe it's an external process that you have that you're communicating with. So technically, it's not I/O in the sense that that process is using CPU, but from your perspective here on this side of things, it is just I/O. I'm just waiting for another process to return something the same way I'm waiting for a database to respond or a web API to respond. It kind of looks the same as the person that's doing the cooperative multitasking. And so the key here is that we're waiting for some I/O operation to complete. And those are the good times where we can say, yeah, pause now this code execution and go run something else. So now we need to talk about workloads, because we need to characterize the type of work done by a chunk of code. What kind of work is the process dealing with the majority of the time? Well, we could be spending a lot of time running computations. And this means that we would benefit from a more powerful CPU or a more powerful core. So this is something that is basically a CPU workload. It's computations, and we need a lot of the CPU in order to run our code. But we could also have a chunk of code that, a process or even a thread or a task more generally that spends a lot of time waiting for I/O to complete. So this is where we're waiting for I/O. We're waiting for something. We can't use the CPU because we're waiting on something to finish, and then we can start using the CPU again. So that would not benefit from a more powerful CPU or a more powerful core. And this would be an I/O workload, right? So we've kind of characterized things in these two broad buckets: CPU workloads, I/O workloads. Now, most workloads are mixed, right? You're going to have a mix of doing something, doing some computations, then making a call to an API, waiting for that, and then making some more computations. But generally, you'll find that in your code, you're going to have dominant bottlenecks, either going to be CPU or I/O. And then we characterize, therefore, those as CPU bound. If the main bottleneck, if what's really slowing a certain part of our code down is CPU, then we say that that code is CPU bound. On the other hand, if it's basically taking a long time to run because it's waiting for some I/O to complete, like a web API call or a database call, then we say that we are I/O bound. So these are the two types of workloads. So let's talk about CPU bound workloads in Python using multithreading. So the first thing, of course, is we're assuming that this particular workload, right, it could be a function or it could be, a method inside a class or some piece of code. We're assuming that it's CPU bound, so it's CPU intensive. It needs to do a lot of calculations. We're also assuming that it's possible to write that same piece of code concurrently, like we saw with the average much earlier on. So running these fragments, so if we could take that workload and write it into concurrent fragments, then running fragments using multiple threads would seem like a good solution to increase performance. Run those things in parallel, right? But you can't. You've got the GIL, remember? The global interpreter lock. The threads will run interleaved. They are not parallel. So we do not run threads in parallel across multiple CPUs or cores. No parallel execution. I'm repeating that because that's really key. So now, so we've written the process, right, the particular piece of code in a concurrent way, and we're firing off all these threads, but they're only going to execute one after the other, never in parallel. So we really haven't gained anything by multi-threading that CPU-bound workload. But not only that, but now we have the cost of context switching as well. So in general, that means that our code is actually going to run slower than if it was single-threaded. And I did an example video that shows that also in this channel. So this is why multi-threading in Python for CPU-bound workloads isn't going to help you improve your performance. In fact, it's going to degrade the performance more than likely. Okay, so if threading isn't going to work, anything else that we can do? Well, we can use multiprocessing. So one way to spread CPU-bound loads across multiple CPUs or cores is to start multiple parallel processes. Remember, processes are independent things, and they can run on any of the CPUs or any of the cores that we have. So Python calls this multiprocessing. Now, what's important here is that the process state, as we talked about earlier when we discussed processes, is not shared. Processes are independent. This means that communicating between the main app and the other processes that it's spawning is more difficult or costly than with threading because there is no shared state. Threading was easy. You had access to shared state. Whereas with processes, that doesn't work that way. So in Python, your main application can spawn multiple processes, and it can pass data to a spawn process, and it can get results back from a process. The technical term for this is called marshalling and unmarshalling. Or if you want, in some cases, people talk about serialization and deserialization. The problem with that, it's really not scalable. Because if you think about using multiprocessing in Python, you're limited to the number of CPUs or cores of a single machine. Sure, you could create more processes than there are CPUs, but now you're not guaranteed to have this parallelism anymore, right? Because, well, if you have 2 CPUs and you're creating 3 processes, well, you know that at least 2 of those processes are going to run on the same CPU. So it's going to use interleaving, right? It's going to use time slicing to run the threads there. So you really cannot scale a multi-process application in Python beyond a single machine. Now, in modern computing, and with ever larger data sets that we have to work with, scaling limited to a single machine is often not sufficient. So this means that in reality, although you can use multiprocessing to take full advantage of a single machine, if you need that level of performance where you're saying, well, running on a single CPU is not enough, then it means that you're likely going to need to write more complex code to scale across multiple machines anyway. And again, I have a video that kind of talks about a very simple way of doing that using workers and using a queue to distribute the work across multiple machines. But the point is that I think multiprocessing in Python is nice, it's great, but if you're dealing with problems where you need to scale beyond a single processor, you're probably going to need to switch to a different strategy anyways so that you can, scale across multiple machines. Which may mean you don't even need multiprocessing, maybe. I mean, I've seen cases where you have, Python applications that are distributed across multiple machines, and each distributed piece of code uses both multiprocessing and threading to try and really squeeze as much out of that particular machine as it can. So it really all kind of depends on your circumstance. So now, what about I/O-bound workloads? In Python, of course, and using threading. Well, remember we said, right, CPython is inherently single-threaded. It will only run one thread at a time. Yeah, you can multi-thread, but only one executes at a time. But since most of the time in I/O-bound workloads is spent waiting for an I/O operation to return something, running code concurrently kind of makes sense, even if it is single-threaded. Switching to another thread while one is waiting for I/O means that other code fragments can be executing when they would otherwise have been blocked. So for example, let's say we have these two threads, thread 1 and thread 2. So thread 1 starts doing some work. So this is some CPU work, right? It's running on the CPU, it's doing calculations. And now it makes a request for I/O. So now it has to wait for this I/O operation to complete before it can continue its work. Well, that's a great time for thread number 2 to start running. And it's got some CPU work to do. And then all of a sudden, the I/O completes for thread number 1, but thread number 2 is still kind of running. It hasn't been interrupted yet. And now it's waiting for I/O, and it gets interrupted. The scheduler says, oh, you're waiting for I/O, I'm going to switch you out. It will also switch the thread out if it's been running for a certain amount of time. But if it knows it's waiting for I/O, it's going to switch. So at that point, it's going to switch back to thread number 1, and it can start doing its CPU work again. It can continue on its merry way until it gets switched back. In the meantime, thread number 2, the I/O may be completed. Thread number 1 is still running, and then at some point, it switches back to thread number 2, and it does some work. So you'll notice that in this area over here, we were able to do some CPU work on another thread, while this one was basically paused because it was waiting for I/O. Same thing here. During this time period, waiting for I/O and I/O complete, we were able to actually do some CPU work on thread number 1, right? So you can see that this is going to improve performance, but that's because it's an I/O-bound workload. Now, there are dangers to multithreading. Multithreading concurrent I/O-bound fragments should improve performance, yes, but writing multithreaded code is difficult. One of the problems is that it's preemptive. We don't know exactly when a thread will be interrupted. So we have to be particularly careful with shared state. It is very easy to run into problems. It's easy to make mistakes when you write multi-threaded code, and it's very difficult to debug. Let's take a look at an example. Let's say that we have a bank account, and we have a shared state for an account called balance. And let's say that we have two operations that we want to do. We want to deposit $500 into the account, and we're going to use thread number 1 to do that. And then we're going to withdraw $100 from the account, from the same account, but that on thread number 2. So you could think maybe it's two things coming in from ATM machines at the same time or what have you. It doesn't really matter, but we have these two operations and we're going to kick them off in separate threads, and we're going to kick them off at the same time. So what is each thread going to do? Well, it needs to read the balance. For thread number 1, it needs to compute the new balance, which is the balance that it just read, plus 500. And then it needs to update the balance to a new value. And then thread number 2 is going to basically do the same. It's going to read the balance. It's going to compute the new balance by subtracting $100 from the balance. And then it's going to update the balance to the new value. Right? So that's what those two operations should do. So let's take a look at scenario number 1. So remember, we have the shared state balance. Let's say the initial balance is $500. So now we have thread number 1, which is for depositing 500, and we have thread number 2 for withdrawing 100. Let's say that the code runs this way. The thread number 1, thread number 2, thread 1 starts, and it reads the balance, which is 500. It calculates the new balance. It's a deposit of 500, so the new balance is 1,000. And so it sets the balance to 1,000, and then it's done. Then at some later point in time, thread number 2 starts running. And it also completes its work. It reads the balance, which is currently 1,000, because remember it was set here to 1,000 in thread number 1, and this is a shared state, so it's just reading this balance. It calculates the new balance, which is 900 when we withdraw 100, and it sets the balance now to 900. So once those two threads have completed, our ending balance is $900. And that's correct. That's the way it should be. So now let's look at scenario number 2. Again, we'll start with the same shared state balance with an initial balance of 500. Again, we're going to have our two threads, one to deposit, one to withdraw. But let's say things now run this way because of the preemptive multitasking. Thread number 1 starts running and it reads the balance in, and it's 500. But now it gets interrupted. And thread number 2 starts running. It reads the balance of 500. It computes the new balance, which is 400. And at that point, it gets interrupted. Thread number 1 resumes. So now the new balance is the old balance that it read, which was 500, plus 500, which is 1,000. And then it has time to set the balance to 1,000. And then it's done. And then thread number 2 continues running. Well, it calculated its balance to be 400. The next piece of code it has to run is, well, set the balance to 400. So once those two threads are done running, our ending balance is 400. And of course, that's wrong. You could also have this scenario. Again, we'll start with the same thing. We'll have the same threads. But now things are running this way. Thread number 1 reads the balance and calculates the new balance. Thread number 2 reads the balance, calculates the new balance, and sets the balance. It has time to do all three operations. So now the balance is 400, right? And then the top thread runs and sets the balance to 1,000 because it finishes running things. So now the ending balance is 1,000. And again, that is wrong. Now there are other scenarios as well, some of which will produce the correct result and some the wrong result. Now it is possible to guard against such issues. We can look at locks and queues, and there's all kinds of mechanisms that we can use to basically, make sure that this kind of behavior doesn't happen. But the problem here is we have preemptive multitasking, we have shared state, and the order of the operations here matters. And remember, in concurrent programming, we typically want to make sure that out-of-order execution returns the same result all the time. That's not happening here. There's a problem, right? So multithreading things is quite difficult, right? You have to be really, really careful. So the preemptive nature of the threads and the shared state is kind of causing this issue. So what about cooperative multitasking? So we saw that writing multi-threaded code can be difficult. And we also know that multi-threading in CPython does not help with CPU-bound workloads, right? In fact, it's going to probably slow things down. But cooperative multitasking can help with IO-bound workloads. So things like, multi-threading or other kinds of multitasking in Python that are still going to be single-threaded can certainly help with IO-bound workloads. So is there a simpler or safer alternative for writing concurrent code for IO-bound workloads, right? Because really, the only thing we can hope to improve in our Python app, short of doing multiprocessing or scaling across multiple machines, is really improving performance when we have IO-bound workloads. And the answer to that, of course, is yes. And this is where asynchronous programming comes in. And Python implements that. There is an async IO module, as well as keywords like async, await, yield, and so on. Now, it is a form of cooperative multitasking, because in our code, we specify exactly where a task can be paused and another one allowed to run. So it's no longer preemptive. It's no longer something else coming in and saying, hey, I'm going to pause you and run something else. We specifically say, it's okay to pause now. If we don't say that, it's not going to get paused. It's only going to get paused or switched, basically, when we say it's okay to do so. Now, this is still single-threaded execution. We are still in Python. We're still stuck with the GIL. We still have essentially one thread at a time. But we can still significantly improve the performance for the IO-bound workloads for the same reason that we saw just now when I had those two threads running with an IO-bound workload. We get the same advantages with asynchronous programming, but it's cooperative instead of preemptive. So Python async programming offers an easier or safer alternative to multithreading. I personally feel that writing async code is much simpler than writing multi-threaded code. Now, both async and multithreading are inherently single-threaded, but the performance improvements are going to be for I/O-bound workloads primarily, just as with multithreading. It is safer than preemptive multitasking, but it does add some complexity to our code. It's actually easier to start threads than it is to do some async work. So we need to write concurrent code, of course, just like we did with multithreading or even multiprocessing, right? You need to take your algorithm and make it into a concurrent algorithm, but that's conceptual. But unlike threading, we have to explicitly let Python know how the different fragments can interrupt each other and work together. So this adds a little bit of complexity because now we have to deal with blocking versus non-blocking code. Blocking code is code that basically just has to execute sequentially. Non-blocking code is where you're running a piece of code and you're saying, hey, go and run this. And while that's running, it's okay to pause me and go do something else. Basically, I/O and an I/O operation, right? So it's generally simpler overall than multi-threading. At least that's my opinion. It is definitely easier to debug. But it does require third-party I/O libraries to be async enabled, right? Because if you're going to write asynchronous code in Python, then it doesn't help if the code that you have, the libraries that you have that do I/O operations are blocking. If they're not async as well, then they're going to block. And therefore, your whole thing is getting blocked. Your whole application is getting blocked by that. So it does mean that we need to look for alternative third-party I/O libraries that are async capable. So how does async work? Well, very roughly. The basic idea is that we register concurrent code fragments that will run code and intermittently indicate that a particular line of code would be a good time to interrupt the function that's running. So these calls to async-enabled functions are called tasks. And we end up by creating a collection of these tasks that need to be executed. So these are async tasks, they're async functions. And we're going to, these are based on async functions. And we basically invoke these functions, but they don't run right away. We kind of say, we're going to call this function with these parameters, but not yet. We're just going to define all the things that we want to do. They're going to go inside this collection of tasks that needs to be executed. And of course, tasks would come in and out as your program is running, but let's keep it simple. So then Python creates an event loop, which is single-threaded, and it basically fires off all these tasks. But it only runs one task at a time, right? We are single-threaded after all. So it runs one task. Then at some point, the task indicates that it is ready to be switched, or maybe it just completes. But usually it's ready to be switched because it's waiting for what? For an I/O response, something that's not going to be using the CPU. So at that point, the event loop gets control back because the task essentially that was running goes back and says, hey, I'm paused for now. So the event loop gets the control back and it maybe starts running another task or starts, resuming another task until that task indicates it is ready to be switched or it completes. And basically the event loop just keeps doing that again and again and again, and it will continue that until all tasks are completed. At that point, all your tasks are done. So when a task runs, it is executing code, and at some point it should yield control back to the event loop. Functions or tasks that run and do not yield control back before they have completed are called blocking tasks. Now, it is usual for tasks to contain some blocking code. I mean, after all, we do have some computations to do. But as long as we yield control once in a while, especially when we are waiting for I/O, that is fine. Now, we could yield control even if everything is CPU bound. We could still have concurrency using an async I/O event loop, but we're really not going to gain any performance improvements. The only performance improvements that we're going to gain is if we can do some CPU workload while we're waiting for an I/O to complete. So this means that to get the most benefit from async-based concurrency, we need to be able to yield control, not block, when performing I/O operations. Many libraries are available that implement non-blocking I/O. Like if you're calling a database, well, you could use the library called psycopg2 that is for Postgres. That's primarily a blocking database. So if you use psycopg2, you're probably going to be using blocking calls. And that's not good if you want to make, an async enabled application that also has, that also is going to await responses from the database and do some computations in the meantime. But you do have this new version of psycopg, which is version 3, and that has real support for async, for non-blocking async operations to the database server. Maybe you're making an HTTP request, and if you've been doing that in the past, you most likely have been using the requests library. Again, that is basically a blocking HTTP call, but there is a non-blocking equivalent to the request called AIO, Async IO HTTP. That's basically a non-blocking equivalent to the requests library. Same thing if you're, let's say, reading and writing Python queues, right? Queues are very important in processing. Well, the queue module has a queue in there. Now that queue is thread safe, so you can use it safely in multi-threaded applications. But it is not async, it is blocking. So the Async IO module also implements a queue, but that one is not thread safe. However, it is async enabled. So now you can push and pull from the queue or wait for things to come into the queue without blocking, right, your whole code. You're basically going to say, well, I'm waiting for an item to pop into the queue so I can read it. And well, if there's nothing, I'm going to give control back to the event loop and it's going to continue on its way. At some point, it's going to call you back again. And at that point, maybe it's like, oh, I have an item, right? I received an item. So now I can continue processing. So for most libraries, you have these async versus non-async equivalents. But of course, not all libraries. So to recap what we've covered in this video, we looked at multiprocessing, multithreading, and async. Multiprocessing, remember, no shared data between processes, whereas multithreading and async, we have shared data, which means easy access and very cost-effective access to the shared data. Not so with multiprocessing, where we have to pass data, we have to marshal and unmarshal data between processes. That is a relatively expensive thing to do. But on the other hand, with multithreading and async, we need to worry about shared data. And some of the problems that I showed earlier with shared data and multithreading, well, you can also run into similar situations with async as well. So you always need to be really careful when you're looking at, accessing global variables, essentially. So multithreading is preemptive, which means the operating system decides when to switch. So that means that you have to be really careful when you're writing code because it could get paused at any time. And especially with shared data, you can run into problems real quick. With async, though, being cooperative, we decide when we can yield control back to the main event loop. So we have a little bit more control over when that happens. So multiprocessing is useful for CPU-bound workloads, right? Whereas multithreading and async are really only useful for performance improvements in I/O-bound workloads. The disadvantage on the async is that it does require, I/O code and libraries to be async aware. On the other hand, if let's say you're dealing with a library that's not async aware, you can still kind of wait for things to happen. Let's say it's the request. Let's say it's making an HTTP request, but you don't have an async equivalent. Well, multithreading can actually help you there because you could, basically write a thread that's going to run that request. And then once it hits the IO request, it's going to get stopped. It's going to get paused by the scheduler and your other thread is going to run. So threading could be useful in cases when you just don't have the async equivalents for certain libraries. And of course, threading could be useful for other use cases that have nothing to do with performance improvement. Because I think the other danger is that we talk about concurrent processing, sometimes purely from a performance standpoint. And it's really not. I mean, there are certain cases where you just want code to run concurrently. You're not particularly interested in making it run faster. Maybe you've got a main application that's running, and maybe it's listening for events. The user typed in a number or they clicked on a button somewhere. Well, you're not really talking about improving speed, but it's probably going to be much easier having a separate thread, let's say, listening for user input and doing something, responding to something on the screen, right? But it's got nothing to do with performance improvement. Or you may have an application that's running, it's doing something that's just computationally intensive, and at the same time you want to write, you want to send a heartbeat out so that something that's monitoring it is able to know that, hey, this program is still running. Well, the easiest way is probably to use two threads. One thread that's going to run your actual code, your CPU-intensive code, and another thread that's going to just send the heartbeat out. That way you don't have to worry about putting that inside the main code. You just kick off both threads and, the scheduler is going to essentially preempt the threads occasionally, and you're going to keep everything going, right? So multi-threading isn't just for performance improvement. There are other use cases too. All right, so hopefully this gave you kind of, an overview of what all these things are. Whether it is multiprocessing, multithreading, async, preemptive, cooperative, the scheduler, right? And all those things. And hopefully that will help you make a more informed decision on what you want to do with your Python application. Do you want to use multithreading? Do you want to use async? Do you want to use multiprocessing? All right, thanks for watching.